Hello again. Welcome to another installment of Dave Does Calculus at Home. Today we're talking about section 9.3. Section 9.3 is our very brief introduction to differential equations. We're going to talk about one very, honestly, kind of narrow kind of differential equation, and we're going to talk about how to solve that specific kind of differential equation. And we're going to talk very briefly about what differential equations are. But rest assured, differential equations as a topic is vast. There are many different courses you can take to learn how to solve differential equations. And I imagine that if you're going into engineering, you will eventually take most of them. Differential equations is a big deal. So in class, Monday I think it was, a while ago in class, I gave my very brief introduction of what a differential equation is, and I want to very briefly review that in this video, which is recorded. Differential equations is like the algebra of calculus. And what I mean by that is in elementary school mathematics, you start with numbers as objects, and then you do arithmetic as operations on those objects. So you start by counting things, and those are numbers, and then you start adding, subtracting, multiplying, dividing, exponentiating, all these operations you can do to these numbers. And those are this is the actions that you take on these objects. And then when you get to algebra, you encounter these cases where known operations have been performed on unknown objects, and the result is known. So here's my known operations here are multiply by 2 and subtract 3. And I know that if I take this unknown number and I multiply by 2 and I subtract 3, the result is 9. So I know the operations, I know the result, I don't know the original number, but the entire point of algebra is working backwards, finding ways to undo these operations so you can work backwards and discover what this unknown number is. And then in pre-calculus, we learn about a new kind of object that we call functions. These are our new objects. And then we learn about a new kind of operation called calculus. Calculus gives us the operations that we use to perform on functions, like taking a derivative, taking a antiderivative, an integral, using fundamental theorem. These are all operations that we use to transform objects into other objects. And finally, you get differential equations. Where you get things, again, this is the, in this parallel, differential equations is the algebra of functions. You get these equations where known operations have been performed on an unknown function, and the result is known. So differential equations is all about trying to work backwards to undo these known operations so that you can discover what the original function was. So it's very much like algebra, except whereas algebra deals with unknown numbers, differential equations, algebra deals with unknown numbers that are connected by arithmetic. The operations being performed here are arithmetic, and you're undoing that to find a number. Differential equations deals with unknown functions, and the operations being performed here are calculus. So these are derivatives. And so you have to undo these calculus operations on these function objects to discover what the original functions were. That is the best description I can give of differential equations, trying to ground it in something very familiar, while recognizing that this probably looks pretty bizarre. So let's talk about some very specific differential equations, and then we can talk more about how to solve them. I think the most common, the most popular differential equation that exists is the equation that models unrestricted growth. So if you have a situation where you have like bacteria in a petri dish, if you give them unlimited food and unlimited space to reproduce, which, I mean, obviously in certain scales is infeasible, but on small scales this is feasible. If you give this bacteria in a petri dish unlimited food and space to reproduce and resources, they will grow in an unrestricted way. And you can model this growth very easily using a differential equation. Bacteria grow when they reproduce, and the number of bacteria that reproduce is some fraction of the number of bacteria you have. So, you know, certain bacteria reproduce very fast. You might have some that, you know, each bacteria will reproduce once every 3 or 4 days. You might have bacteria that reproduce once every week, but it's some fraction of the bacteria you have are always reproducing, and that's what gives you new population, bigger population. So you can model this particular unrestricted growth situation by saying that the rate of change in the population, or if y is a population function, y is a population at time t. So this is a function that will change. It models the population at a certain time. If you start with 100 bacteria in a petri dish that you're counting by hand, and then you wait a week and you count how many you have more, you'll get, you know, your population value is changing. Probably it's increasing if you're feeding these things. So the population is your function. The derivative of that function represents how fast it's changing. So the rate of change of this function is proportional to the population itself. So proportional means is a constant multiple times, and y is our population function. So if you start with 200 bacteria, you're going to get a rate of growth that is some multiple of 200. Probably this will be some fraction. And if you start with 100, your growth will be half of that. If you start with 400, your growth will be twice as many. This is a very standard relationship here. This same model can be used to look at your bank account. If you have a savings account that's earning interest, the amount of increase you get in your bank account is proportional to how much is there. This can also be used to model radioactive decay. When things decay radioactively, the amount that decays over a period of time is always a percentage of how much is there. So if you start with 100 grams of radioactive material and it decays, 100 grams of radioactive material will decay twice as fast as 50 grams of that same radioactive material. So that relationship is always follows this model, where the change in the amount is proportional to the amount. So this is sort of like our baseline differential equation. And here's how we're going to solve this. I'm going to replace y prime, because we've talked about this notation. Y prime was Newton's notation. For most of Calc 2 we've been using Leibniz's notation, which instead would be written as the change in y over the change in t. So I'm just going to change it to that. K is a constant. Let's say that K is, let's say that we know what K is. Let's say the K is 0.1. So however much you have, your rate of growth will be 1/10 that amount. So if this is modeling a population of bacteria, then your y would be the number of bacteria, your t would probably be in days. This is a bacteria that produces once every 10 days. So 1/10 of your population is cloning itself every day. So this would be a good model for bacteria. If you have a bank account that's giving you 10% interest, tell me where your bank is. For a bank account, your K value would be a much smaller number, like probably 0.01% or something like that. If this is a radioactive decay situation, your K will be negative because this value is decreasing. It's not increasing. But this 0.1 is a reasonable number for unrestricted growth of a bacteria population. So I have an equation now that looks like this. This is my differential equation. It involves a derivative of some unknown function, and it involves the original unknown function. This is what we got so far. Here's how we're going to solve this. This is a special category of differential equation that is called separable. I might be spelling separable wrong. It's the version of separate. It's the adjective for separate? Sure. Something that can be separated is separable. This one can be separated. All I have to do to separate this is divide both sides of this equation by dy. Oh, no, sorry. I need dy to stay on top. I apologize. dt that needs to move. I'm going to multiply both sides of this equation by dt. Which will cancel this and leave me with dy equals 0.1 y dt. And then I'm going to divide both sides of this equation by y. Which will leave me with dy over y equals 0.1 dt. So this is what I mean by separable. It is possible through algebraic manipulation to completely separate all of your y business on one side of the equation and all of your t business on the other side of the equation. Or sometimes these will be x's. Sometimes you'll be separating y's from x's. Sometimes you'll be separating other variables. In this case we have y's and t's, so we have all of our y's on one side, all of our t's on the other side, and we've accomplished this by multiplication. So here's the benefit of something being separable, and why a separable differential equation is sort of the baseline introduction. Here's how we solve these things. Once you have these separated, all you have to do is take an antiderivative of both sides of the equation. That will solve this whole derivative thing and leave you with a function, and we can talk about what that looks like. I'm going to erase some of this stuff over here. Okay. I'm going to take antiderivatives of both sides of this equation and see what that looks like. The antiderivative of dy over y is the natural log of y. The antiderivative of 0.1t is, or 0.1 dt is 0.1 t. If we're being extremely pedantic, both of these integrals are indefinite and both of them need a plus c. But I don't need to use two arbitrary constants. If I put a plus c on both sides of this equation, the very next thing I would do is subtract it from one side and just have a different arbitrary constant here. So I'm just going to use the one arbitrary constant on that side of the equation. What I have here, this thing, is a implicit solution to this differential equation. It's implicit because it's not solved for y. Stuff is happening to y. But it's a solution because there's no derivatives left. So I've solved the differential equation, sort of, by getting rid of all the derivatives. I can keep going. What I need to do next is solve for y, because I would really like to have an explicit solution for this. So you can get rid of a natural log by raising both sides as exponents on top of e. So e to the natural log of y is going to just give me y. This will give me, on the right, I will have an e to 0.1t plus c. This is now an explicit solution to the problem. I'm going to keep going one more step of simplification here, because I want this to look very pretty. Again, this particular style of differential equation is extremely common. This models population growth, bank account growth, radioactive decay. This models temperature change, thermodynamics. This has an enormous number of applications, and because it's very, very common to see, I want you to see it in the form that it is most commonly presented in. And so for this, the next step is to, for simplifying this, I'm going to split the exponent on the e. So what I have here is y equals e to the 0.1t times e to the c. I'm actually going to call this c1 because I'm going to get some other arbitrary constants involved here. So addition inside of an exponent is the same as multiplication between two exponents with the same base. So I can split that into two different e's. And now one of these things is a constant raised to an arbitrary constant. And I'm going to simplify this just by giving it a different name. That is some other arbitrary constant c. We can call this one c2 times e to the 0.1t. So, the unknown function whose growth behavior is modeled by the equation, rate of change is proportional to amount present. This differential equation is solved by an exponential function. Exponential functions are the